Alright, so this is round 2 of equilibrium. So we're on our second equilibrium chapter. So chapter 16. This is part 1 of our lesson video series. There will be many in this chapter. And so today I'm going to cover sections 16.1 and 16.2. So we're just going to grin, we're going to bear it, we're going to pretend like not just me loves equilibrium and that you who are watching this also love it. And we're just going to accept it. Remember, K is just products over reactants. If you just think of it in basic terms, it's a little bit easier to swallow when we go into the more difficult stuff. Alright, so don't worry, we're not going to start with super difficult stuff right now. A lot of this stuff you already learned in honors. We're going to go a little bit into acids and bases like we did in honors. So let's just all accept that this is happening and we're going to love it. Alright, so 16.1, let's do a brief review of acids and bases because I'll assume you might have forgotten some stuff. So remember, acids taste sour, they react with metals, and they change the color indicators. Remember, they can also be strong or weak electrolytes, so we'll have to discuss which acids are strong and which are weak. Bases, on the other hand, taste bitter, feel slippery, and they will also change the color of an indicator. However, it would be a different color than an acid, otherwise the indicator wouldn't be very good. And then bases, again, can be strong and weak. Alright, so we got to make sure we know which is which. So, Arrhenius definitions for acids and bases. An Arrhenius acid is a substance that increases the concentration of H plus when dissolved in water. So for example, HCl, when you dissolve it in water, is going to break up into H plus and Cl minus because it increases the H plus, or a lot of times we call this the H3O plus hydronium ion, because of course that's what it is when it bonds with a water molecule. That's considered an acid. So if it increases H plus or H3O plus, like I said, we'll use these interchangeably, then it's considered an acid. An Arrhenius base, on the other hand, is a substance that increases the OH minus concentration. So like NaOH, when we put that in water, it breaks up into Na plus and OH minus. And so since it's going to increase the concentration of OH minus, it is considered a base. So, already on to section 16.2. So see, 16.1 wasn't that bad. So now let's jump into Bronsted-Lowry. So the Bronsted-Lowry definitions involve the transfer of the H plus ions, which sometimes we will call H plus a proton. Because hydrogen has one proton, most of them have 0 neutrons, and then 1 electron. If we remove the electron to make it positive, what we're left with is 1 proton. So sometimes H plus will just be called a proton. So Bronsted-Lowry's involve the transfer of H plus ions from one substance to another. And so like I said, H plus is sometimes called a proton. H3O plus, like I just showed you on the previous slide, is called the hydronium ion, and it forms when water gains an H plus. So if an H plus is released by an acid, it will attach to water, making H3O plus. So like I said, we'll use H plus and H3O plus interchangeably. So a Bronsted-Lowry acid is a substance that donates a proton or an H plus to another substance. So you can see in this reaction we have HBr and we have water. Now we have H3O instead of H2O, and we have Br minus. So what's happened is HBr donated its hydrogen to water. So see, water got the extra hydrogen, so it turned into H3O, and HBr lost the hydrogen, so it's now Br negative. And then a Bronsted-Lowry base, wow, this was poor color choices on my part. There is NH3 right here. I don't know how well you can see it. I can't see it very well in real life, and it's red. So for some reason, I thought putting red font on an orange background was a great idea. So what can I say? I know chemistry, but clearly I'm lacking in the common sense area. All right, so that's okay. I'm not trying to teach you common sense. I'm trying to teach you chemistry. So a Bronsted-Lowry base is a substance that accepts the proton or H plus from another substance. So let's say we have NH3 and H2O. Well, on this side, it becomes NH4 positive and OH negative. So what happens is water gives the NH3 one of its hydrogens. So in this case, NH3 is accepting a hydrogen, so it's a base. And I will go ahead and tell you one of the most common weak bases that we'll use is NH3. So you might just want to commit that one to memory. It's a weak base. NH3 is. Alright, so we don't just focus though on acids and bases, we also have to focus on conjugate acids and bases. Alright, so to be a Bronsted-Lowry acid, the substance must be able to lose an H plus ion. So for example, it might say, could this be a Bronsted-Lowry acid? Well, obviously not. It doesn't even have hydrogen, so it has nothing to lose. Okay, it's got to be able to lose a hydrogen. So like for example, HCl, H2SO4, H3PO4, any of those would be Bronsted-Lowry acids. And then to be a Bronsted-Lowry base, a substance must have a non-bonding pair of electrons to bond with an H+. So that's why I say that NH3 is our most common weak base, because it looks like this. So what will happen is when that H+ comes in, it will form a bond just like that. So like for example, if it said NH4, and of course that would be positive, could that be a Bronsted-Lowry base? Well, now there's no more lone pairs to accept another H+. So at this point, this could not be a Bronsted-Lowry base because it doesn't have the ability to accept any more hydrogens. So a substance that can act as an acid or a base is called amphiprotic. An example is water, because water can accept and become H3O+ when it accepts a hydrogen, or it can lose a hydrogen where it becomes OH-. So water is an example of something that is amphiprotic. It can act as an acid or a base. All right, so now let's talk about these conjugates. So again, we covered this in honors, but you might need a little review. So a conjugate base is formed when an acid loses a proton. So for example, if I have HCl and it loses that H+, the Cl- would be my conjugate base. Okay, so once I take away one proton, notice it says when it loses a proton. Okay, the reason I point that out is we can't say, like if I have H2SO4, if it loses 2 hydrogens and I have SO4 - 2, that is not the conjugate base of this. It's only when it loses 1 hydrogen. So it would be a conjugate base if we did this. We have 1 H+ and then the hydrogen sulfate ion right here. This would be a conjugate base. So you can only lose 1 proton. All right, and then a conjugate acid is formed when a base gains a proton. So for example, if I have NH3 and I add water, and it's going to make, NH4+ and OH-. See, this is when the base has gained 1 proton. So this would be the conjugate acid right here. All right, and then a conjugate acid-base pair is a pair of substances that only differ by 1 proton. Can't differ by anything else. Okay, so let's look at this reaction down here real quick. So here we got to look at kind of what's going on. So I have HNO2 and H2O. I'm making NO2 negative and H3O positive. So I can clearly see that this is donating its hydrogen to the water. Hang on, I might already have all this animated. Oh, well, let me not draw it then. Okay, so we can clearly see that HNO2 is donating the hydrogen to the water. But, okay, I wasn't ready for that side yet, so I guess we'll do that next. So since HNO2 is the donor, it's the acid. Since water is accepting the hydrogen, it is acting as the base. Remember, we talked about it's amphiprotic. All right, it's not basic normally, it's just in certain situations it can act as an acid or a base. So then we have to look at what happens when we go the opposite direction. Like if we go in the opposite direction, we can see that H3O+ is going to give that hydrogen back to NO2. So now in this case, this is acting as the donor, which would be the acid, and this is acting as the base because it's accepting. All right, and so then I just look and say, okay, well here was the acid originally, here it is once it's lost an H+. So this would be my conjugate base. And then here's water originally. This is what it looks like when it has gained a proton. So this would be my conjugate acid. So if a question asks you to list a conjugate acid-base pair, you can either grab the acid and its conjugate base, that's a pair, or you could grab the base and its conjugate acid, that's a pair. And so notice they only differ by 1 hydrogen. All right, so hopefully that's not too difficult to understand. All right, so let's look at the first part together. So it says, what is the conjugate base of each of the following acids? So we know acids need to lose an H plus. So the important thing to remember is when you lose an H plus, the charge also gets altered. Okay, so I'm going to get rid of my hydrogen. It was neutral, so if I lose an H plus, now it has a -1 charge. All right, here I'm only going to lose one hydrogen. Okay, I'm not going to lose both. So since I lost one H positive and it's neutral to begin with, it will have a -1 charge. Here, I'm going to lose one hydrogen only. Now, because it was positive, once I lose an H plus, it's just going to be neutral, so it'll be pH3. And then here, I'm going to lose that hydrogen, so it becomes CO3. It was -1, but since I lost an H positive, it becomes -2, just like that. All right, so if you're going to a conjugate base, you just remove one hydrogen. Now, on the other hand, this one says, what is the conjugate acid of each of the following bases? So these are going to gain a hydrogen, but because, again, hydrogen's positive, that's also going to alter the charge. So this is going to become HCN. It was -1, but I added a +1 hydrogen, so it's now neutral. This, even though we're used to crossing charges, so normally we would add 2 H positives, remember, conjugates only differ by 1 hydrogen. So I'm going to add 1 hydrogen. Now it was -2, but with that positive hydrogen, it's just going to be -1. All right, water. I'm going to add that hydrogen. It was neutral, so with that +1, it just becomes +1. And then HCO3 is going to become H2CO3. It was -1, but with that positive hydrogen, it will now become neutral. Okay, so hopefully none of those were that bad. Again, equilibrium is really not that bad. You just got to give it a chance. All right, so y'all tried this one. I'll assume you've done that already, and we'll look at it together. So it says, write the formula of the conjugate acid for each of the following. So remember, conjugate acid means it has gained an H+. So don't forget to alter those charges. So HSO3 is going to become H2SO3. Since it was -1, it will now be neutral. F negative is going to become HF. Since it was -1, it's now neutral. Remember, even though you're tempted to put H3PO4 because you want to go ahead and cancel your charges, conjugates differ by 1 hydrogen. So it's HPO4. It was a -3 charge, but we only added 1 positive. So that's going to change it to a -2 charge. And then last we have CO. So now it's going to be HCO. It was neutral, so since I've added a positive hydrogen, it would become positive. All right, so hopefully you got all of those right. Really, most of the time, the thing that I notice is not altering charges correctly. All right, so let's look at our second sample exercise. It says the hydrogen sulfide ion HSO3 negative is amphiprotic. So that means it could lose this hydrogen or it could gain a hydrogen. Either one is an option. It says write an equation for the reaction of HSO3 with water in which the ion acts as an acid. Identify the conjugate acid-base pairs. Okay, so it's telling me I'm starting with this. I'm reacting it with water. And it told me it's acting as the acid. That means it's going to donate a hydrogen. So it will drop down to SO3, but now its charge will be -2. And it's going to give its hydrogen to water. So water would become H3O+, the hydronium ion. All right, so now I just got to label everything. Well, it already told me it's acting as the acid, and it donated. Since water accepted, it was acting as the base. And so then, remember, the acid, once it loses a hydrogen, is the conjugate base, and the base, once it gains a hydrogen, is the conjugate acid. So I could have answered with, these would be my pairs, in other words. My pairs would be HSO3 negative and SO3 -2. That's one of my pairs. Or one of my pairs could be H2O and H3O+. Okay, those would be my 2 pairs. And so notice each of them only differ by 1 hydrogen. And that's it. That's all you got to do. And conjugates are going to become super important, especially when we get to titrations. Alright, so other part says we'll write the same reaction but pretend like the HSO3 negative is acting as a base. So I start out with HSO3 negative. I'm going to add water again. But this time it said it's going to act as the base, which means water is going to donate a hydrogen to the HSO3 negative ion. Alright, so that means it's going to become H2SO3, and when water loses a hydrogen, it just becomes hydroxide, OH negative. Alright, so this time, since it's accepting, it's the base. Since water is donating, it's the acid. And so once it gains a hydrogen, it is now a conjugate acid. And once water loses a hydrogen, it is now a conjugate base. So of course our pairs would be this, because they differ by one hydrogen, and this, because they differ by one hydrogen. So you'll always have two pairs. Like, you can't only have one pair. There's got to be two. Alright, so let's look at our next one together. Oh, whoops, I'm not even looking at it. Boy, I feel like I'm moving so slowly. Oh, this is practice. We're not looking at it together. I'll assume you paused it and already tried this one, and now we'll look at it together. So when lithium oxide, which is Li2O, is dissolved in water, the solution turns basic from the reaction of the oxide ion, which is O-2, with water. Okay, so in other words, it's telling me the O-2 ion is going to react with water. Write the reaction that occurs and identify the conjugate acid-base pairs. Now, even if you're not sure, like, okay, well, what is the reaction going to be? I don't know what O-2 and water make. Well, it has told you it turns basic. If something turns basic, that means you need to form OH negative. Okay, so that, you got to use sometimes the wording. Like, if they're making you write a reaction that you wouldn't necessarily have memorized, then a lot of times their wording will give you hints on what your products are going to be. Okay, so we start with our O2 negative, and we're going to add water to it. Okay, and remember, it tells that the reaction turns basic because of the O negative 2. So that means I know that O negative 2 is going to act as the base, and it's going to accept the hydrogen. So when that happens, it becomes OH negative, and when water loses, it also becomes OH negative. So of course you could put, 2 OH negative if you wanted to. So anyway, so now let's identify those conjugate acid-base pairs. Well, here, since the O negative 2 is accepting, and obviously it couldn't donate too. Like, if you were wondering, like, well, how was I supposed to know it wasn't going to donate? Well, it doesn't have a hydrogen. It can't donate. So it's acting as the base. Since water is donating, it's acting as the acid. And then because these are the same, it doesn't matter. Okay, let's just pretend like these two go together. All right, now it's accepted, so it's the conjugate acid. And now this one has lost, so it's the conjugate base. So our pairs would be the O negative 2 and OH negative, and the H2O and OH negative, just like that. Alright, so that one was a little tricky only because you got 2 OH negatives, and so that can throw people off sometimes. Alright, so let's talk a little bit about strong versus weak. So a strong acid or base fully dissociates into ions in solution. A weak acid or base, oh, that should say only. There we go, now it does. Only partly dissociates into ions in solution. So this is what strong would look like. Let's just say this is HCl. Okay, you can see all the H's and Cl's break up. All of them. Okay, that would be a strong acid. Whereas let's say this is HF. If you look, yes, there are a couple that have broken up, but most of them are staying together. Okay, so that means this is not going to make as much H plus as this would, even if you start with the same amount of particles. Alright, so that's the difference in strong and weak. And it's odd because you want to think, oh, well, the strong would obviously stay together. Well, no, it's strong because it makes a lot of H plus. Okay, that's what makes it more acidic. So if an acid is strong, then its conjugate base is weak. Boy, I'm like full of typos. I should have its right here. Alright, so if an acid is strong, so like here we have HCl is very strong. Cl negative is negligible as far as even acting as a base. It barely acts as a base at all. Okay, whereas here we have HF, it's not quite as strong. F minus starts having more strength. Here we start having very weak acids, and then the conjugate bases start getting strong. So it's like a seesaw. One's strong, the other's weak. If an acid is weak, then the conjugate base is strong. Okay, so you can see this goes from weak to strong, but this goes from weak to strong going down though. Alright, so when we're talking talking about strength. Sometimes they just like to give you a reaction and ask which one is the stronger acid or stronger base. So if H2O is the stronger base, then X minus, then the equilibrium will lie to the right. Okay, so if H2O is the strong one, then equilibrium goes in this direction. All right, it says if H2O is the weaker base, then equilibrium lies to the left. So if X minus is the stronger base, it's going to go this way. So in other words, y'all, the reaction will always proceed away from the stronger acid or base. Okay, so that's what you need to pick up from this. All right, so of course, if we start talking about what direction a reaction's going in, that hooks us to equilibrium and our K value. So equilibrium favors the transfer of a proton between the stronger acid and stronger base to form the weaker acid and weaker base. Okay, so we're going to go from strong to weak. It always favors moving on to the weaker side. All right, so let's look at our first one together. So it says, for the following proton transfer reaction, use figure 16.4 to predict whether the equilibrium lies predominantly to the left and K is less than 1, or predominantly to the right and K is greater than 1. Okay, so all I need to do is go through and compare. So I have HSO4 and I have SO4. All right, so I'm going to click back. This is the chart they're talking about. So HSO4 and SO4 are right here. So if I look, HSO4 is almost strong. SO4 is very, very weak. Okay, so let me go back and label that. So HSO4 is, whoops, going in the wrong direction. So this is my stronger one. This is my weaker one. All right, so that means I automatically know we're going to go from strong to weak. Remember, K is just products over reactants. So if I'm interested in increasing my products, that means K would be greater than 1, just like that. Okay? So, hopefully that one wasn't that bad. That chart is what helped us get that answer. All right. So, y'all try these two real quick. So, I'll click back to the chart and then I'll give you a chance to pause it and look at it. So, here's your reactions. Here's the chart. I'll assume you paused it and tried it now. I'm going to have to click back a couple of times. Sorry about that. All right, so we're comparing HPO4 and H2PO4. So, I go back. I can find HPO4, let's see, where's H2PO4? Here it is, H2PO4 and HPO4, right here. All right, so if I look, this is the weaker, okay, because see how strong is way up here. This one's a little closer to the weak side. This one's a little closer to the strong side. So HPO4 is a little bit stronger than H2PO4. Alright, so HPO4 is the stronger than the I think I said H2PO4 was stronger than the HPO4. Alright, sorry, they were very close to each other. Alright, so H2PO4 is stronger than the HPO4 from the chart that we just looked at. So in other words, remember, it's going to go from strong to weak, so it's going to favor the reactants. Since K is products over reactants, if I favor reactants, K is going to be less than 1, because of course reactants is in the denominator. Alright, so let's go back and look at our other one. So hopefully you got that one right and didn't mix it up once you clicked back like I just did. Alright, so we have NH4 positive and NH3. So I find, let's see, where's my NH4 and my NH3? Here we are. Oh, of course it's like right where I wrote. Okay, it's right here. We got NH4 and NH3 happening right here. And now if you ever get two, like I just happened to pick those two, like you could pick the other two. You could compare OH minus and H2O if you wanted to. It doesn't matter. You can pick either set. Okay, so we could compare H2O and OH minus if we wanted to. Like once you start getting near the middle, it starts getting a little hard to decide. So here we could just pick this one because it's further on the edge. And so we can see that clearly OH is stronger and H2O is weaker. Okay, so here, we'll just do it that way. So that way if you ever get some there in the middle, you can kind of figure out what's going on. All right, so I know that this is my strong and this is my weak. So So of course it goes from strong to weak, and since K is products of reactants, in this case we favored products, so K would be greater than 1, just like that. All right, so hopefully you got both of those right. All right, and so we are done for today. So see, we didn't even get a lot into equilibrium. Really, we're just talking about acids and bases. We barely even got into K values. Okay, so see, this chapter isn't that bad to start with. All right, you got this. We all got this.